Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the chemistry topics, and this is solubility. I'm going to begin with diffusion. Diffusion is the movement of substances from a region where they're highly concentrated to a region with low concentration. So the first part is going to be for diffusion in gases. The gaseous particles spread out into certain spaces by this process of diffusion. And when this occurs in air, we say they are diffusing through air. Like I said already, diffusion is a spreading out of particles from a region of high concentration, meaning where the particles are more in number or in amount, to a region of low concentration. These particles continuously spread out until they are in equal concentration throughout the whole space or container. Gaseous particles move in a straight line, but because they come into contact with other particles in the air, the collision with those particles can change their direction, and that is why even if they diffuse in a straight line, they are changed due to the particles they collide with, and so it takes longer for them to spread out through the whole space, maybe a container or in a specific room. That can be seen here. If we begin with this particle, moving from here to here, it could move to here, bounce into another particle and go there, go there, go there, go there, go there, go there, and finally come here. The distance it was supposed to move is really short, but because of the collision with the particles in the air, it takes longer for the molecule to travel. Here we have two experiments to showcase diffusion in gases, and these are very common in the exam. The first example is diffusion of bromine in air. If we begin with bromine gas in the lower apparatus and just air in the upper one, but there is a material separating the two, if that material is removed, like in this case, then the bromine is going to diffuse into the air and the air is going to diffuse into the bromine. So diffusion causes the concentration of both particles, meaning the air particles as well as bromine, to be uniform at the end of the diffusion, so the color is going to be the same. We see this is orange-brown, and this is basically colorless, but in the end we can see the color becomes lighter because the air has mixed up with bromine. The other example is diffusion of ammonia and HCl to form ammonium chloride. This experiment is set up by soaking cotton wool into ammonia solution and by soaking cotton wool into hydrochloric acid. Because they're going to be in concentrated state, gases or vapors are going to come off. So we will see HCl coming off from there, and ammonia is going to come off from here. But because ammonia is smaller in size, or it has a lower molecular mass, it travels faster in comparison to HCl, which has a higher molecular mass. You know chlorine is 35.5 and hydrogen is 1, so this is going to be 36.5. While here nitrogen is going to be 14, 15, 16, 17, these are going to be 17, so it travels faster in comparison to hydrogen chloride, and that is why the product of the reaction between the two forms closer to HCl and farther away from ammonia, because ammonia was able to diffuse faster due to the lower molecular mass. Next we go to diffusion in liquids. Diffusion in liquids occurs very slowly if there is no mixing. In this experiment we see potassium manganate 7 that is diffusing through a liquid. In the end, we will have the whole solution having the same color because uniform concentration has been attained. The potassium manganate 7 is going to find it harder to diffuse through the liquids because I say the particles are closer in comparison to the gases, so it takes longer for diffusion to occur. But we can speed up the process of diffusion by mixing. So if you get a stirrer and mix here, the diffusion is going to occur faster. Or if we increase the temperature, the particles are going to move faster and the diffusion is going to occur much faster in comparison to without mixing. Now for solids do dissolve in liquids, and we can study their solubility. However, for solids, we have to consider a solute, a solvent, as well as a solution. A solid, which is the solute part, has to first dissolve in the liquid, which is the solvent, in order to form a solution, and this solution is going to diffuse through the specific liquid. Like I said already, if we have that containing a liquid, and this is the solid cannot diffuse because it's held together. We have to first make this solid dissolve to create a solution, and then we have this concentrated solution in this area diffuse through the whole liquid until uniform concentration is attained. When the solid dissolves, the forces of attraction between the particles have to break. I'm talking about the old attractive forces which are between the solids. And again, I'm going to explain this again. We have this liquid and we have the solid sample. For this solid to dissolve, it has to break the forces of attraction between the solid particles, meaning the solid particles have to separate so that they are uniformly distributed within the specific volume of solution, and then they can spread out because they'll have more ability to move. So these old forces attracting the solid particles have to be broken so that the new forces of attraction, these are the ones between the solid and the liquid, are formed. So here we will have the tiny solution within that corner before it diffuses. So for solid to dissolve, the new attractive forces should overcome the old attractive forces, meaning the forces of attraction between the solid and the solvent should be greater than the forces of attraction between the solid and the solid in order for dissolution to occur. Also, solubility depends on temperature. For solids, the higher the temperature, the higher the solubility. So the definition of solubility, this is the mass of a solid which must dissolve in 100 grams of a solvent at a particular temperature. This is very important because solubility is temperature dependent. Like I said already, the higher the temperature, the higher the solubility of a solid. So here we're going to be looking at an example of an experiment that studies solubility of a specific solid, and this is carried out at 40 degrees. In this experiment, we are using potassium nitrate as the solid. So we will begin by weighing the evaporating basin. We need to know the mass of the empty evaporating basin, and then you note that mass down. Then we will heat the boiling tube to above 40 degrees. The reason for heating above 40 degrees is to allow a certain mass to dissolve, because our actual experiment is going to be at exactly 40 degrees. So heat slightly above 40 degrees and then add the ionic solid in the water and stir rapidly until no more dissolves. Then after that, we are going to let the solid cool to just 40 degrees Celsius. This is the temperature at which we're going to carry out the experiment. And then at that temperature, we're going to decant some of the solution into the evaporating basin. You do not need to take away the particles that are solid at the bottom. Just decant off the top like you can see here, so that a certain volume is poured into the evaporating basin. Here they say this was already weighed to be 25.72 grams. And now we're going to weigh the contents like we see here. You weigh the evaporating basin containing the solution on a scale. The mass 58.00 grams is the mass of the evaporating basin plus the solution that has been added. Then after that, the evaporating basin is going to be heated so that some water gets off. This is so that crystals can be formed. And we see we are not using direct heating. We are heating the water, and then the steam coming off the water is heating the evaporating basin so that some water can be evaporated. This is to ensure that crystals begin to form. And we heat to constant mass. This tells us that there is no more water coming off. After that, we will record the final constant mass of the basin and the dry solid. We can see this is 38. And that means the difference between that and that is going to be the mass of the water. So the mass of the actual solid is going to be the mass of the evaporating basin plus solid minus the mass of the empty evaporating basin. And to calculate solubility in grams per 100 grams of solvent, this is going to be the mass of the solid, which we get by subtracting this minus that, divided by the mass of the solvent, which we saw the difference between that and that, which is 20 grams, times 100, and that will be our solubility. So this brings us to the end of this video, which was talking about solubility. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.